Okay, thanks, Paul. So I'm going to be giving a couple lectures, and the title of this series is Noncommutative Geometry. Maybe I'll just Smoothness and Fukaya Categories. Today's talk is really going to be more about noncommutative geometry and smoothness and a little bit less about Fukaya categories, and we'll talk more about symplectic. I mean, I'll mention them and how they fit into the story, but we'll start really developing applications on Friday of all this picture. Okay, so what is this? What sort of noncommutative geometry do I mean? I'm just going to keep this first talk relatively introductory, and obviously it's a very large topic, so I'll just mention a few things. So there's this proposal in this form, probably due to Kontsevich, that we should replace the study of X, and by X I mean some sort of algebraic variety, by the study of a certain DG category, C sub X, which is its category of perfect complexes. Okay. Okay, so, or rather, maybe I should study the geometry of X via some study of this category. So implicit in this is somehow that, okay, the point of this proposal is somehow that many geometric structures in X and many properties of X are actually reflected completely faithfully by some property of this category. Okay, so properties like smoothness or properness, which these are the things I'll be talking most about today, and structures, some sort of de Rham cohomology groups, things like vector fields and forms, at least when interpreted suitably cohomologically, actually just depend on this category. So we didn't need to think about X having some sort of commutative structure. We just needed to remember this category. Okay, so they're reflected faithfully by this category, and that's great because now we can study them for this category. And now there are many situations in which we can get categories not from just some algebraic variety, and we can study these structures on such categories too. Okay, so so they can be studied, by properties and structures on this category, and now we can study them for C other DG or A infinity categories of interest. Okay, for instance, as my title suggests, Fukaya categories are related sometimes to these categories by homological mirror symmetry, but we might want to study these properties, independent of this relation. Okay, so our goals, what do I want to talk about more specifically? Today I'm going to talk specifically about basics of noncommutative geometry, in particular smoothness, but I'll give nearly equal attention to properness, but it's somehow much more well known, and how it arises in examples of interest, such as perfect complexes, but also other categories like Fukaya categories. And okay, so part 2 will be some sort of thought exercise. Okay, according to this philosophy, we should see most structures on X in terms of some structure on this. So how do we see a particular structure on X, the Mukai pairing? So there's some pairing on differential cohomology of differential forms on an algebraic variety, a proper algebraic variety. And there's a purely categorical way to get it. It's introduced by Shklyarov. And so the thought exercise will be, how do you see this purely categorically? I won't prove it's the same as the Mukai pairing, but it'll have all the same properties, so seems believable. Finally, we'll apply this and some new twisted versions to Fukaya categories. So here, at this point, we're considering a category that's no longer coming from an algebraic variety, so it's very important we could think of things non-commutatively completely. Okay. So this is the plan for, hopefully I'll get halfway through 2 by today's talk, and then the second half will be Friday. Okay, so setup. So now I'm going to forget for a while that there was any algebraic variety lurking around and just talk about some general things about DG or A infinity categories. So we'll start with a field K and C some sort of DG or A infinity category over this field. I'm not going to maybe completely review the definition of what this is. If you don't know what an A infinity category is, think a DG category. And I'm going to keep the talk, as formula free as possible, so you don't have to worry too much about the A infinity formula yet. So okay, maybe I should have some notation, so we will indicate this is the chain complex of morphism spaces. Maybe I'll assume always and implicitly that C is, okay, so I'm going to actually be cohomologically graded. I doubt it'll come up very much, but just by convention, the differential increases degree by 1. And I'll assume that C is what we call cohomologically unital, meaning if I pass to cohomology, maybe I'll just, if I pass the cohomology of all morphism spaces, they're identity morphisms, so it's a usual category. Okay. All right, anytime we have a DG category, we have a category of modules. Okay, so this is it's some canonical enlargement of C, and I say it's an enlargement because there's a canonical embedding of C into modules. Okay, so modules are functors from C up to chain complexes, where I should think now of A infinity functors, or if I want to get the right category, and I just want to think about differential graded functors, I think about DG functors, and I mod out by, I pass to some sort of homotopy type category, I mod out by quasi-isomorphisms. So A infinity functors are, okay. So there's some enlargement like this, and what is the Yoneda embedding? Okay, so there's a canonical functor given by taking Hom with an object. Okay. So in mod C, we have a nice sorry, did I get the variance wrong? Should this be Hom into K or something? Yeah, indeed, because it's C up. Yep. Great, I agree. It's covariant in C, and sorry, and it's covariant in K and contravariant in this, so it's a Hom functor from C up to K. Okay, so we have perf C sitting inside modules of C. Okay, this is the split closed pre-triangulated envelope of C. Okay, what do I mean by that? It's the smallest subcategory of modules which contains the Uneda image of C. And well, modules has this sort of, I can take sums, shifts, cones of modules, and so on. So I just take the smallest category that contains this and is closed under finite cones and retracts. Okay. Okay, so this is sometimes, whenever you have some sort of split closed pretriangulated envelope, they're unique up to quasi-equivalence. So this, if you're used to other constructions of this sort of envelope, this agrees with some other construction. But we don't maybe care about that for this talk. Okay, so in fact, for the purposes of non-commutative geometry, we're more interested in this category than we were in C. I mean, we kind of care more about properties of C that are detected by this envelope of C. Okay, so that didn't matter what C was inside it. Okay, so a couple basic definitions. We say a subcategory of C split generates C if, well, there's an induced map on perfect complex categories of perfect complexes, and if this is a quasi-equivalence. Okay, so what does it mean? It means in this category of modules, every object of C is isomorphic to a retract of a finite complex of objects of A. Okay. And if we have a pair of categories that aren't necessarily one is contained in the other, I might say that they're Morita equivalent. And for the purposes of this talk, I just mean that there's a quasi-equivalence between their categories of perfect modules. Okay, maybe just a comment if you're used to the usual category of algebras and modules. If you have an ordinary DG or A infinity algebra, yep. Oh, sure.
So this, does anybody want to ask whether this is the same as mod A being mod B? Yes, John wants to ask. And the answer is?
Yes.
Yes.
Because perf A and perf B are uniquely characterized as compact objects in mod A and mod B.
You mean the cohomologies of these complexes are isomorphic?
Sorry, when I write, what I mean is there's some functor in which is an isomorphism on cohomology of morphism spaces.
Okay.
And it's essentially surjective on cohomology also. But the functor exists on the chain level.
Okay. And that's weaker than having an actual homotopy of the complexes matching them up?
Well, these are categories.
They're categories.
But the morphism spaces themselves are actual complexes. So.
Oh, we're working over a field.
Oh.
So define a homotopy inverse.
Oh yeah, yeah.
So,
I forgot
so
about that.
Yeah.
this is morphism symmetry.
Yeah, yeah. Great. Yeah. So I'm working over a field to avoid issues like that. Absolutely.
This would be a good moment for anybody else to ask questions.
Can you say again why the answer to that question was yes?
Okay, so maybe I should say it's a known. Okay, I'm not going to talk about this so much, but there's a notion of a compact object in a category, and perfect complexes over A can be characterized as compact objects in the category of modules over A. So if you have some equivalence between mod A and mod B, which is the traditional notion of Morita equivalence, you can pass to compact objects and get an equivalence between perf A and perf B. And the other way is a lot easier. The other way, you just pass to modules over perf A and modules over perf B, which, this modules over C is the same as modules over perf C. There's sort of no problem.
More?
Okay, so if we have an ordinary algebra, we can think of it as a special case of this story, because of course we can think of it as a DG or A infinity category, A, which has one object, which I'll always denote by point, and the morphisms are the algebra. Okay, and under this correspondence, modules over this category are the same as ordinary modules over the algebra. Okay, because if I have some functor from A to chain complexes, I can associate a module over this morphism space by seeing what that functor does to point. Okay. Okay, so this is kind of the thing we care about. We care about maybe C up to Morita equivalence. Okay, so we care really about perf C more than C. But now to work with it, we need a way of getting at what are functors from C to C, or rather from perf C to perf C, things like that. And so it's necessary for what I'll describe later to introduce a notion of bimodules. Okay, so if I have a pair of categories, by category I mean DG or A infinity, I can introduce a category of bimodules between this pair of categories. Okay, and well, by definition, a bimodule is a bilinear functor from C times D op to chain complexes. Okay, what do I'll say what I mean by that in a second. Let me just point out that okay, so I'm being careful about what I'm saying here. There's a notion of an A infinity bilinear functor if you're familiar with the A infinity literature. But if you prefer, you might prefer to think of this as ordinary functors from this tensor product of categories. Which makes sense when the categories are DG. Okay, so there's this notion of functors. What is it? What are these things really? Okay, so an object, a bimodule B, is given by some data. Okay, for every x, for every pair of objects, I have a chain complex. Okay, and then there are some multiplication maps For instance, multiplication maps you should think of as the map induced on morphism spaces. So for instance, there's a map from if I have a morphism from x naught to x, that gives me a map from the bimodule of x naught y to the bimodule of x y. Or this is how you might think of this as a multiplication map, but you could also think of it as a map from this functor perspective. It's a map from Hom x naught x to Hom chain complexes B of x naught y, B of x y. Okay, and there's some multiplication. That's a multiplication on the left. There's a multiplication on the right. There's some higher stuff. They satisfy some coherences. I won't worry too much about that. Okay, so why do we care about bimodules, and what are the bimodules we specifically care about? So first of all, bimodules between C and D are responsible for functors. They give the functors between module categories. Okay, and some of these bimodules give functors between the perfect complex categories that we actually care about. So these provide a nice way of accessing, functors from a category to another, or at least from their split closed pre-triangulated envelopes. Okay, so what is the functor? It takes a module to its derived tensor product over C with the B. Okay. So and here I'm supposed to, what I suggest you do is, for a while, if this language is unfamiliar, you think of bimodules as just usual bimodules between a pair of algebras. And if I have an A module, I can get a B module by tensoring with an AB bimodule. Okay, that's exactly what this is. It's just a multi-object version. Okay, so maybe I should say that if you like algebraic varieties, you should think of something like quasi-coherent sheaves on x times y as inducing. There's some analogy, or rather precise correspondence. It's quasi-coherent sheaves on x times y are something like bimodules, and they induce some sort of convolution operation. Okay. So in all the examples, I'm just going to take C equals D. So I'm just going to consider CC bimodules. And what are the examples that I care about? If I have KL, a pair of objects, then there's a canonical representable or Yoneda bimodule. YKL. And what functor from C times C to chain complexes is it? Something like this. Okay, so if A is a DG algebra as a special case, then this is like the free module, A tensor A up. Okay. Now there's a canonical. There's always a canonical CC bimodule which I call the diagonal bimodule. I denote C sub delta. C sub delta of xy okay, there's some order reversal, but don't worry too much about that. It's just Hom. Okay, so C sub delta is the Hom functor. So Hom is the usual bilinear functor from, it's the first bilinear functor you might think of between C and itself to chain complexes. Maybe there's some, this isn't strictly in the thread of the main talk, but there are some operations you can perform on bimodules. So if B is any bimodule, you can associate a linear dual bimodule B check. By taking the linear dual of the chain complex associated to by the original bimodule. Sorry?
You reverse the order.
Yeah, I have to reverse the order. That's right. So maybe I want something like xy, and here's yx. Okay, if B is any bimodule, there's another type of dual called the bimodule dual, B shriek. Okay, and its values on a pair of objects KL are R-Hom. Okay, so R-Hom means my Hom in the category of bimodules. So it's some sort of Xed type group, except the chain level. So I take Hom from my bimodule to the free bimodule, corresponding to K and L, and that's what B shriek is of KL. Okay. So here, I'm supposed to think, continuing this analogy. So I had the free module. I had the diagonal. So if A was a DG algebra, I had the diagonal bimodule, just A. You can think of that as, of course, an A tensor A app module. Here, if I have a bimodule over A, I can take its linear dual. And if I have a bimodule over A, I can take R-Hom in the category of A bimodules, which is A tensor A app modules from B to the free module, the free bimodule. Great. Only under certain conditions. So, so yes, go ahead.
So if B is okay, so this is for C equals D.
Yes.
So for probably usually B dual DC.
Is a DC bimodule. Yeah. So B is a CD bimodule. B dual is a DC bimodule. That's right.
Sorry.
I was saying if doing it twice, even if it doesn't quite give you an inverse, will be in some sense an inverse of the homotopy?
No, so you should think the analogy you should think for vector spaces. The double dual of a vector space isn't equal to the vector space unless you're finite dimensional.
Will there be an analogous finiteness condition here?
Great, that's the next thing I'll define.
Okay.
Wait.
Yep. Other questions? Yep.
So this B shriek is also for CD bimodules?
Yeah, good question. So sure, you can take, well, let's think about this for a second. So if I have a CD bimodule, let's just do it for algebras. I don't think there's, so I can take R-Hom in the category of CD bimodules. From here we go. So yeah, I think again it produces a DC bimodule. Okay. So I didn't say what the bimodule structure on this new thing is, but the bimodule structure comes. So I took R Hom with this free thing with respect to the outer product, but there's an inner product that survives, and that's responsible for the bimodule structure. And as we can see, the inner product is a right C action and a left.
I mean, it really is just for a single category. So you're applying regular duality to an enhancer product.
Sorry, what do you mean?
Well, this is also a special case of taking like C to be vector space.
Yes, that's right. That's right.
So are there any cases where those two dualities the same? Or?
So they're never the same that I'm aware of. However, sometimes the bimodules that they
Maybe for finite dimensional, the category of finite dimensional chain complexes. Or something like this.
oh, maybe for vect you're saying they're the same.
Certainly for K.
Yeah.
For the category that's just
Sure.
one object.
Sure.
is in the board.
Okay, in some trivial cases they're the same, but in most non-trivial cases
Is
they're
there
very
a
different.
morphism between them? Between the two duals?
Let me say what I know there. I mean, they're inverses under suitable finiteness conditions. Okay, so they're actually,
Oh,
I mean, they're not actually the same. But yes, go ahead.
Just a notational question. What do you mean by the superscripts that are left and right arrows in the last line you wrote?
So I guess what I mean is, when you say R Hom of bimodules, you should say what is the bimodule action.
Yes.
Okay, so I'm taking R Hom with respect to this bimodule action. So C tensor D has a CD action and a DC action. Right? It has this, outer CD action. Maybe I'll just say it this way. It has this outer CD action and it has this inner DC action. Right? So I'm specifying that I'm taking R Hom with respect to this bimodule structure. And the bimodule structure in green survives. So it gives this. Okay, sorry. There's a. Maybe I should. Okay, so maybe I should say.
So you're going from thin arrows to thin arrows.
Well, no. I'm eating up the thin arrows. So the thin arrows are being eaten. And yes, that's right.
Input output.
so again, very naively, should
Yes.
think of those two dualities as having a graded vector space. You can take the usual dual and then some kind of graded restricted dual where you dualize every graded component. I mean, or
You mean for this one you're saying?
Yeah, just trying to understand the sort of the difference between the two.
Right. Okay. Well, this one I think is more straightforward for vector spaces. Okay. If you have a vector space here, and you take Hom into a tensor product of frees. Yeah, I mean, it feels very much the same in this instance, but no. I mean, I think the differences between this dual and that dual come from the differences between C and K. So if C is like K or perf K, okay, you won't see tremendous differences.
I see. So maybe. Okay. All right. Okay.
But this B shriek is a Morita invariant
Yeah,
notion.
that's right. Shriek is a Morita invariant notion.
And the check is.
Well, that's
B
also-
check is too. Yeah, B check is. That's right. So these are all. I mean, somehow the. Okay. Well.
I mean, let's say.
Yeah. No, I agree. I agree. It's some Morita, some Morita invariant involution in the bimodule category. That's okay.
Is there a little speech you can give about B shriek?
A little speech. I can give a speech about C delta shriek, the diagonal bimodule shriek. This is sort of some operation on any bimodule, but if I apply the operation to the diagonal bimodule, I think that's something I can maybe say something about. Okay, so we call Okay, so we can apply these operations in particular to the diagonal bimodule. I think that's where I was going next. Okay, so if I apply them to the diagonal bimodule, I'll just drop the delta notation. So I'll call C check, C delta check, and C shriek. C delta shriek. Okay, and there's a special name for these two bimodules. This is often called the Serre bimodule. And C shriek is often called the inverse Serre bimodule. And the reason for this is, in good cases, some cases of which I'm about to describe below, under some finiteness conditions or so on, for x, for a category of perfect complexes, tensoring, so the functor given by tensoring with C check corresponds to tensoring with the canonical class, shifted by, maybe shifted by dimension. Okay, so this is some dualizing operation that corresponds to a very familiar operation on perfect complexes. And similarly, under nice cases, tensoring with this inverse, this bimodule dual of the diagonal bimodule is the same operation as tensoring with the inverse Serre. Okay, and in cases in which both are defined and both correspond to this, you can see by comparison with commutative case that they're inverse. They induce inverse functors. Okay, so maybe I should, as we've already seen, these operations, aren't maybe very well behaved unless there's some finiteness conditions satisfied by the bimodule. So let me just tell you what those finiteness conditions ought to be. So bimodule B is proper if the chain complex associated to any pair of objects has cohomological finite dimension for any pair of objects. Okay, so in other words, if B, instead of being a bilinear functor from C tensor C op to chain complexes, it maps from C tensor C op to perf K modules contained inside chain complexes. These are chain complexes with finite cohomology. Okay. Okay, so if B is proper, then its linear dual is proper too, and the double dual coincides with the original bimodule up to quasi-isomorphism. Okay. Okay, so B is perfect if it is split generated by Yoneda or representable bimodules. Okay, what do I mean by that? I mean that, okay, well, we had these analogs of free modules, okay? And if B could be built out of free modules by some finite, as a retract of some finite complex, then we say B is perfect, okay? So this is the same as B, a retract of a finite complex of frees. Okay, by retract I mean summand.
You wrote free for a differential grade layout or differential grade algebra.
Yeah, so this is, by free I mean one of these.
Oh.
Maybe projective is a better word. Okay, so if the claim is that if B is perfect, then actually B shriek is perfect too, and B double shriek coincides with B. Okay, so if B is proper, B check check is isomorphic, is quasi-isomorphic to B as bimodules, and if B is perfect, B shriek shriek coincides with B, and in particular B check and B shriek are both perfect as well.
What about the converse?
Sorry?
What about the converse? Can you have a double dual in either sense isomorphic to the original guy without having those conditions? Or is it?
In the first case, no.
In the first case, no. In the second case, I didn't think about it. But I might hope no as well. Hmm? Ah, thanks. OK, great.
What was the comment? Oh, it's not smooth. Yeah.
OK. After all this, I can tell you what it means for a category to be smooth or proper. So if I have a category, we say the category is proper if its diagonal bimodule is proper. And the category is smooth if its diagonal bimodule is perfect. OK, sometimes compact is used instead of proper, but just in case you're looking at the literature. OK, so there's some very explicit finiteness condition, and we apply it to the diagonal bimodule. And this gives us what it means for a given category to be smooth or proper. OK, and so the remark is, as with these operations of duality, being proper or smooth is a Morita invariant property. OK, so these are Morita invariant properties of a given category. So they only depend on the category of perfect complexes. Anything Morita equivalent inherits smoothness or properness. Questions about the definition? So we're going to do some examples.
If E is a ring, then being proper and perfect corresponds to the category of perfect complexes being proper and perfect?
Yeah, that's the first example I'll do.
So you apply to the perfect.
Yeah, I'll do an example, and I'll mention coherent as well. What is going on with coherent complexes? Other questions before I? So yeah, I think the first thing to do is to see why this is a sensible thing and why it corresponds to the usual notion of smooth and proper. OK, so in algebraic geometry, let's say we have X in algebraic variety over C, if you don't want to worry too much, or a finite type separated scheme over a perfect field, if you do want to worry. And now, for in this case, this is a reasonable, this notion of smooth and proper coincides with the usual. So first of all, if perfect complexes of X is proper, well, that's true if and only if X is proper. Yep.
A silly question: when you equip perfect complexes with the geometrical structure, do you pick some kind of check covering?
Yeah, you can pick a check covering or use injectives or something. I mean, I think there you have various options,
Right.
and they're all equivalent. That's right. So importantly, this is as a DG category. Okay, so I'm not gonna. I'm not going to prove all of these because then I'd completely run out of time, but maybe I can give you some references where you can look things up. So I'm sure this is earlier. This appeared earlier, but you can find a sort of very careful proof of both sides of X being proper if and only if the category perfect complex is being proper in a recent paper of Orlov called Noncommutative Geometry something. Maybe someone else knows an earlier reference. This result, the result on smoothness, as I understand it, is due to Luntz. And maybe let me actually try to explain that for a minute. Yep. OK, one direction is, yep.
I'm being somewhat dense.
I mean, this is completely classical. I mean, there's nothing, I mean, maybe. Yes, maybe I should say exercise. Yes, that's right. It's an exercise depending on what you mean by algebraic variety. Yes, but it comes like directly from definition of what a proper scheme is. Oh.
You don't use the value of criteria?
I think to go from, to go this way you don't, to go that way you do, I think. So
when you have a curve, you can always fill it in.
Yeah, so Orlov's proof does, for instance, to go this way.
So we have to, so if X is proper, then perf X is proper.
That's very easy. Yeah, that's very easy.
Okay. And if X is non-proper, I just take the structure sheaf O. Or you say, to show that if O, if the ring of functions is one-dimensional, it's proper, I'm using the valuative criterion.
Well, it's not just the ring of functions. You have to use all modules.
Was it?
You have to use all modules.
To show for any two perfect modules.
No, but I'm trying to
get-
show that X is not proper, therefore perf X is not proper. So you just have to find one object for which
Take the forward of an affine curve.
Yeah, that's right. So you use the valuative
Forward of
criterion.
an affine
Exactly.
curve.
Exactly.
But why don't I just use O?
That doesn't extend. Yeah.
What do you mean extend? I'm trying to show that if X is not proper, perf X is not proper.
Like Lev said, take A2 mod the origin, then the ring of functions is just.
Right. So it depends what we mean by algebraic variety.
Yes.
So I was sort of
For affine, I think
Naively,
for
yes.
affine, I think you're okay
fine.
by your argument. Yes.
Yes.
Okay. So okay, to sketch this argument, I mean, I'll maybe just say like 2 lines about it, but so it's some smoothness of this category, some statement about bimodules. Over perfect complexes, so it'd be useful to have some sort of geometric way of thinking about that. And you can indeed think of them as quasi-coherent complexes on the product with the diagonal bimodule. Corresponding to the structure sheaf along the diagonal inclusion. Okay, so now anything about this being perfect, I can translate into that, a statement about that being perfect. That's okay. Great. So let's just go this way. If okay, let me just call this category. Well, let me just use. Okay, so if perf X is smooth, the structure sheaf along the diagonal, well, it's split generated. So it admits a finite resolution. By tensor products of perfect modules. Okay, and so now you apply. So this is a sheaf on the product. I can apply it to a sheaf on one factor and produce, a sheaf on the other factor. So I apply it to the structure sheaf of any point to get, well, on one hand, this acts by the identity. On the other hand, I equate this with this resolution, apply the resolution to OP, and I get that OP has some finite resolution by Friese. Okay. Okay, by vector bundles or whatever. So that's equivalent. That's a condition for P to be a smooth point. Okay, so if the structure sheaf of that point has a finite resolution by vector bundles, the skyscraper sheaf has a finite resolution by vector bundles. That's equivalent to smoothness at that point. Okay. So in the other direction, if x is smooth, then the product x times x is smooth, and if y is smooth, coherent sheaves on y equals perfect complexes on y. So the structure sheaf of the diagonal, which is a priori coherent, is perfect. Okay. And moreover, there are generation results that say perfect complexes on x times x is split generated by the image of tensor products of objects. Yes, I will now. Maybe I'll just say if x is affine, in this entire discussion you could replace perf x by the ring of functions, a usual algebra, and study smoothness of that algebra. Okay, and that's equivalent to smoothness of spec, of spec of the ring. Okay, so next, okay, so here I use the fact that, perfect complexes. There's complexes of vector bundles. There's another category, coherent complexes, which is not in general equal to perfect complexes when you're not smooth. Nevertheless, on the other hand, there's a theorem of Luntz that says that actually coherent complexes on x, if x is as above, coherent complexes on x is always smooth, no matter how singular x is. Okay, and maybe I'll say even less about why this is true, but it's worth saying a word or two about why we might expect this to be true. Here the point is the structure sheaf of the diagonal is always coherent. And Luntz proved that by induction on the singular locus of x, that coherent sheaves on x has a collection of split generators EI, and moreover that products of these generators EI box tensor EJ split generate coherent sheaves on the product. Okay. In particular, split generate the diagonal structure sheaf. Okay.
Might be fair to say
yes. Word.
or at least with the first statement. That
Yes. Yes. Okay. Okay. So okay.
What are the insiders talking about?
Yeah. How do I? Okay. I may have gotten the spelling wrong. Okay. Sorry. What?
Sorry.
Yeah. No, it's fine. Okay, so Ruquier has results about compact generation of categories of coherent sheaves. And Luntz, okay, I mean, I think Luntz refined it. So he refined it because he produced a collection which satisfies this.
Should we think of it as a statement that coherent X is not an interesting thing to consider?
No, I wouldn't say that actually. I might say that, well, I mean, Luntz's point of view is you can think of, okay, so perf X, if you have a proper but not smooth variety or something, perf X is not smooth. It embeds naturally into cox. Okay, so this is something non-smooth. It embeds into something smooth. You can think of it as a non-commutative resolution of singularities. Okay, so I would say smoothness is actually a highly desirable property that gives coherent complexes a lot of structure and functorialities that perfect complexes may not have. And
so X is above means X is an algebraic variety.
yes, that's right.
Okay. What's the reference for this term?
Categorical resolutions of singularities. Okay. I think theorem 6.3. I mean, I guess I don't want to say too much about this, but if you have sort of like a nodal elliptic curve, you can take the structure sheaf of the singular point, and you can take the structure sheaf of the total space, and Luntz proves by some induction that those generate cox, and their products generate co over product. I mean, you sort of just add objects for every bit of singular locus in every dimension, and you can get that this process terminates at some point. Okay, he has a much cleaner way of saying it. I'm just sort of paraphrasing. Okay, so there are examples of interest just for ordinary algebras that arise in, say, topology. If M is a topological space, I can associate two interesting DGAs. The singular cochains of M and the chains on the base loop space. So this is a DGA with a Pontryagin product. Okay, so with let me just say, with product given by concatenation of loops. Okay, and cochains on M is proper if M is homotopy equivalent to a finite CW complex, and chains in the base loop space is smooth if M is homotopy equivalent to a finite CW complex. Okay, so cochains on M.
Would be false for retract.
Sorry, what?
Would be false. Both would be false for retract with finite CW complex.
Oh, is that right? I mean, I think they're both true, but.
I would guess that the first one would also be true for the retract.
Yeah, that's right. That's right. I mean, I'm stating some oversimple assumptions. Yeah, I think. Yeah, that's right. That's right. So, okay. So I'm not going to worry about that, but I agree they should be true for retracts of finite CW complexes. Okay. So yes.
In this thing of thinking about the non-commutative resolution of singularities, is it true if you take like a singular element variety, if it gets resolution of singularities that?
Yeah. So is there an embedding of perfect complex categories?
So the resolution the same as coherent sheaves down below.
I'll defer to someone who knows much more about this than I
If you
do.
have rational singularities, it's sort of obvious because the pushing around the structure sheet is just the structure sheet. You're going to derive something from the right edge of embeds. But then there's this whole business of trying to find a non-commutative resolution that satisfies that nice condition where pullback is actually admissible functor and embeds this as an admissible subcategory, which doesn't always happen through resolution.
I'm not sure that answered the question. Was the question whether coherent of X, if it's singular, coherent of X is not a proper. So it cannot be the same thing as an ordinary.
Perfect of a proper.
I just interpreted the question as a relationship to resolution of singularities in the classical sense. forgetting about the first line, this non-commutative resolution of singularities versus last resolution.
Yeah, I don't have a good answer, unfortunately, to it.
Does perf x determine of x, like if x and y derived equivalent?
So I think there's a statement that okay. So I can tell you a couple things about that. The answer is no in general, just as categories, but perfect complexes with proper support on X is some sort of Morita dual. So you take sort of finite functionals on cox, so functors from cox to perfect complexes of K modules, and that gives you perfect complexes with proper support. So if X was proper, then perf X is determined by cox. Okay. In general, there's a theorem that perf X with its T structure determines cox, but that's information we don't have access to in the non-commutative world generally. Okay. Yeah, of course. Well, with its monoidal structure, perf X with its monoidal structure determines X, so it determines cox. So I've forgotten about monoidal structures and T structures because, we don't have good origins for them in other settings.
Yep.
Okay. Okay. So and maybe I should say cochains on X in this setting is expected to be never smooth. And chains of the base loop space is expected to be never proper, but I don't actually know whether the results are true, because it's related to the question of, is the homology of the free loop space ever finite dimensional for a manifold? And maybe the answer is, I'm not sure. Okay, I'll leave it at that and we can discuss more later. Maybe I'll say why that's smooth. So the smoothness of this, of chains of the base loop space, it comes from a certain fibration. So if I have a base loop, I can evaluate it at halfway around the loop. It gives me an element of M. And the fiber is two copies of base loops. Okay? And so whenever I have a fibration like this, I get some sort of multiplicative spectral sequence. So this fibration is compatible with multiplication on the right and on the left. Okay? So I get some sort of spectral sequence from chains on M with coefficients in this free module to chains on loops M, okay, which is your free resolution. Okay, let me say it that way. Other questions about all this?
What about co-mod per? Is that always smooth?
Yeah, great. So yes, it's always smooth. So smoothness is preserved by localizations.
Great.
What was the question?
So cox mod perf X is always smooth.
Oh, that's the category of singularities.
Yeah, that's right. That's right. This is db sing, the DG version of db sing, and proper if the singular locus of X is proper. Okay, and I was going to say something about matrix factorizations, but I'll just say this and then. Okay, so the last few minutes I'll start to transition into Fukaya categories. Maybe before that I'll pose a couple more questions that you can ask purely in the non-commutative framework that, to my knowledge, we don't have a completely satisfactory answer to. Okay, so first of all, let me think about a way to say this. Does every non-commutative space, okay, so by non-commutative space I mean this sort of DG category, have a non-commutative resolution of singularities? Okay, so there's a lot of literature on this, including this paper of Luntz. And it's known in a number of cases, especially by reduction to commutative geometry. So by this I mean, e.g., your category, even if it's a bad, poorly behaved category, maybe it embeds into something smooth. And here's a related question. Does every smooth category C? OK, so something you might do if you have an affine variety C is you might like to compactify it. Okay, so you might want to realize it as the complement of some, compact set and some projective variety. Okay, so does every smooth category C have a smooth and proper compactification? E.g., a smooth and proper D with a localization from D to C. Okay, so to pass to some open locus of a compact set is localizing the category along something. So can you find a smooth and proper category that localizes to C? Okay. Okay. Like in commutative cases, we have good answers to this. I think the dream is yes, but I mean, at least I've heard these. Okay, maybe I should perhaps attribute these questions probably to Kontsevich. That's where I heard them. I think there's some hope that yes, but no, basically no methods for how to prove it.
Would you mind if I keep you from transitioning to something entirely different with
That's fine.
5 minutes to go?
That's fine. Yeah.
We just have questions.
Well, I mean, I can say what we expect about Fukaya categories being smooth and proper. Yeah. That's not completely different. But maybe I'll say a minute about that and then we'll do questions. OK, so in symplectic topology, let's say we have a compact manifold. Then we can associate a Fukaya category in nice cases over some field, maybe a Novikov field, but I'm not going to worry about that. And this category is always proper. Essentially completely from definition, because Ham in this category is some sort of Floer complex, which is generated by transverse intersection points, maybe perturbing, so things are transverse, and these are compact Lagrangians. So there are only finitely many intersection points, therefore the chain complex itself is finite dimensional, if I make choices like this. Okay. So we don't have good criteria, like completely general good criteria for X compact when the Fukaya category is smooth, because we don't have Lagrangians for general X. We don't have good constructions of Lagrangians for arbitrary compact symplectic manifolds. So I'll say the Fukaya category should be smooth if we could find enough Lagrangians. Okay, so situations of geometric interest, you'd expect that toric complete intersections or nice types of projective Kähler manifolds should have smooth Fukaya categories, but there aren't completely general methods for producing Lagrangians. Okay, so maybe one word about X non-compact. There's two types of categories you can associate: a Fukaya category of compact Lagrangians, and this is always proper, expected, never smooth, for the same reasons as above. And this expected, it's conjecturally smooth when your symplectic manifold is Weinstein. I mean, maybe I should say work in progress will show that it's smooth when it's Weinstein, because we have there a good candidate class of Lagrangians always, right? So we have like some ascending manifolds or Lefschetz thimbles, which we can, use for enough Lagrangians. Okay, so let me stop there. Yes. Yeah.
So I guess you always mean here that you look at you pass to this category of bounding cochains. I mean.
Oh, sure.
One could ask about these notions for curved A-infinity categories.
Yeah, you can. That's a very good point. Yeah, here I'm thinking about weakly unobstructed. I mean, I'm really thinking about things that give a genuine A-infinity category. And you can indeed ask this for curved objects, and in some basic examples, it does seem to be a meaningful question to ask. But I don't have a good grip on the homological algebra of that yet. Yep.
When you, no, I was just trying to read what you wrote. You wrote, so f compact of x is proper, but
Expected, never smooth.
oh, expected. Okay.
Yeah.
I didn't know.
Maybe let me say exact non-compact symplectic manifold. Okay, and then you have the wrapped Fukaya category, and it's conjecturally smooth always when x is Weinstein and expected never proper. Okay, let me stop there. Thanks.